Me here, and my name is Manoj Shakya, and I'm an assistant professor at the Department of Computer Science and Engineering at Kathmandu University. I did my PhD from Nanyang Technological University, NTU, and Professor Xavier is right there. Hi Xavier. I had an opportunity to take his classes as well. He taught us like deep learning and all those stuffs there back in NTU. I still remember your lectures are still with me, by the way. Yeah, thank you so much. You are a wonderful professor, in fact. But right now he's working. He's in NUS right now. So today, today I'll be talking about reinforcement learning, something that is a bit different than supervised learning and unsupervised learning. I mean, most of you, I'm pretty sure most of you uh, are very close to supervised learning because computer vision and natural language processing and all these kind of stuff, technologies, they follow the supervised learning. RL is a little bit different. And what I assume is like, most of the time when I talk to my students, they talk about supervised learning, unsupervised learning, clustering and all those techniques. But then rarely talk about reinforcement learning because we see that reinforcement learning probably is not that popular, I assume. But then for me, it's a wonderful technology. It's because it learns by doing something, right? It's not like supervised learning or unsupervised learning. In supervised and unsupervised, there are like data, labeled data and unlabeled data. But in reinforcement learning, it's something different and what it is. And some very few foundations, about foundations I'll be talking about in these lectures. So I'm gonna talk almost 1.5 hours, probably 2 hours till 11 a.m. And we'll have a Q&A session as well. So before Q&A session, I hope to make you clear about, let me quickly turn it on and then, yeah. So, so in today's lecture, I'll be talking about reinforcement learning, what it is actually, and then I'll quickly move to Markov decision processes, MDP. If you are not familiar about MDP, it is actually a mathematical representation. Every problem, if you want to solve that problem with reinforcement learning, then you have to, it is better that you represent that problem with Markov decision processes. We call it MDP. It's a fantastic representation of problem, mathematical representation. We'll talk about that one, what it is and how it actually works. And then some core concepts of reinforcement learning. For example, value functions, state value, action value, and Bellman equations. If you are familiar about RL, you have probably heard about this Bellman equation because it's the heart of reinforcement learning. We'll talk about that Bellman equation as well. And exploration and exploitation. This is another very, very critical part of reinforcement learning. We'll also understand what actually this is. And I'll also go through a Q-learning algorithm. It's a off-policy algorithm, and it's one of the most popular algorithms in RL. So I'll talk about this one, and finally, I'll conclude my lecture talking about this reinforcement learning. What makes reinforcement learning deep reinforcement learning? So because basically it's very simple. We have reinforcement learning, we have deep learning, and when we combine them two, into one single, then it becomes a deep reinforcement learning. So these are some of the topics that we are. I'll try to make. I'll try to talk about, and in the later sections, you'll probably you'll be. I think Ronak, Professor Ronak. I'm not sure whether he's here or not right now, but he will have a second lecture today, and he'll talk about RL and then autonomous vehicle. Fantastic application of reinforcement learning actually. So at the end of this session, you'll probably be able to explain to somebody else that what is reinforcement learning, what are the foundations of reinforcement learning. For example, every time I meet some very interested students who are interested in RL, I tell them like, okay, these are some of the core concepts that you need to understand when you want to learn RL. And you'll be probably able to describe what MDP is and how you can translate that problem into MDP as well. And you can interpret what Bellman equation actually is, and also you'll be able to explain what is the trade-off between exploitation and exploration, because every time you deal with RL, you have to deal with exploitation and exploration as well, and you'll be able to explain what DRL actually is. It is, of course, it is the combination of reinforcement learning and then deep learning, but what is the merging point? So these are some of the points or objectives that at the end you'll be able to do. Okay, now let me start with reinforcement learning, what it is actually. So I'm going to give you some of the examples, some of the applications, what it is. But again, I would like to start with this Bellman equation. This is what we call Bellman equation, optimality equation is, and then, I mean, the Bellman equation actually starts from this equation. So here we have this Q value, quality value, expected returns, and then these equations, these terms. So so I'll talk about this later on, but then just to show you that what Bellman equation looks like. Now let me start with some of the applications. We have heard about this game, right? This is AlphaGo. So AlphaGo playing with another champion from South Korea, I believe. This is Lee Sedol, if I remember correctly his name. So if you look at this one, this is the game, and in 2014, I believe, this game was between the champion Lee Sedol and then the reinforcement learning RL, or basically what we call AlphaGo. AlphaGo is an application, or the RL agent, let's say. So it was actually well trained with RL, reinforcement learning technique, and there was this reinforcement learning technique, AlphaGo agent, AlphaGo, and then there was another guy, and they played 5 games. Out of 5 games, 4 games actually were won by AlphaGo, and that was the fantastic moment for reinforcement learning, enthusiastic. So that's when I think my first when I heard about this reinforcement, that was the moment when I first heard about this reinforcement learning. And there is this another moment when reinforcement learning came into the next level. These are Atari games. If you look at these Atari games, so Atari games are actually played by reinforcement learning. It proved that reinforcement learning, basically deep reinforcement learning, DRL in short, deep reinforcement learning became so powerful that they can even win the human in all these competitions, on all these Atari games. So, and then that moment again proved that RL is very, very useful, in fact. And there was this another moment, RL was very, very useful, basically in ChatGPT, LLM, basically LLM, let's say. So how come this RL was integrated in LLM? It was the RL was integrated in LLM for the reason that the RLL actually wanted to learn something from human feedback. And then the people came up with the idea that why not we integrate this RL concept. There is this concept called reward shaping, reward model. So we integrate this reward model into LLM, and then the LLM actually gets feedback from human, and then LLM itself improves, day by day. That was the actually reason why this RL was actually integrated into LLM. And then this was like, for example, GPU algorithm, GPRO algorithm. These are some of the very good algorithms we use for this human feedback looping. So this again proved that RL is in fact very, very useful. But most of us are, when basically even me, when I think of RL, I think of applications like robotics, where robot has to learn walking, when robot has to learn jumping and then dancing. All these things actually, I believe that they have to learn it via reinforcement learning mechanism. So now let me take you to the very fundamental thing of reinforcement learning, how actually it started. So when you think of reinforcement learning, you have to think of 2 entities. Two entities are there. They interact with each other. They communicate with each other. One we call it agent, the other one we call it environment. So when agent is someone who decides or who takes action, certain actions, For example, if you think of RL agent in AlphaGo, so the agent actually decide where to place the chessmen, or what you call that, the item, where to place that one, right? So here the agent actually decides on something and it takes that action. But that action actually happened in the environment, and then the environment actually sends some information to the agent itself. So let me give you let me take this one. So environment actually provides all the information to this agent. If you look at this diagram, this is a very fundamental diagram. Everyone who is interested in RL has to learn this one, actually has to be familiar with this. And then the agent again takes certain action, let's say at any time t, given time t, at is an action. So agent actually takes certain action over this environment. And environment, the state of the environment changes, you see, because there is this certain action happened there, and because of that action, certain things changes over there. But that change may be good for the future or may be bad for the future. But then again, this environment actually provides certain reward as well, based on whether that action was very fruitful. If it is fruitful, if it is good, to get to reach to the objective, then it actually provides certain value, and that value probably is very high or it may be low. So based on that action, the environment provides what we call a reward. You see, basically in the programming, or in any context, reward is basically a numerical value. You see, numerical value. I'll give you examples, but this is a very fundamental thing. Okay, so let me explain. But if you look at the textbook, some of the textbook they refer this in this picture. Agent is there, environment is there. They communicate with each other. Agent takes certain actions. Environment provides state and then reward. So let me show you some other figures as well, because if you go to the internet, probably you'll find different pictures there. For example, if you look at this one, someone reported that this is an agent. It looks like a robot, robot, and there is this environment, and then it actually depicted by this figure, the Earth figure, and you also find this kind of figure as well. Here also they communicate. There is this robot, and this is what we call agent. Robot has to do something over the environment, and it provides certain information regarding state and then the reward. And based on that reward, agent understands, okay, the recent action that I took, that I decided to take is basically good or it is bad. Based on the reward that it receives from this environment, it understands that the action that I just took is a great action. So, probably it will benefit me to reach to achieve the major objective. Or sometimes you might see agent being kind of something like this brain, because agent sometimes not sometimes but most of the time agent is the one that takes action. That's why it has a brain. We assume that one, right? We assume that agent has the brain, it understands everything, and it takes certain action based on their understanding. Let me give you another example. This is also one of the very great examples, applications of RL, reinforcement learning. So here, what does RL do? Definitely RL takes certain actions, certain actions. But for what? To optimize the energy. If you are there to plan the urban planning or something like that, probably you need to optimize so many things. Probably you need to optimize energy, energy. So how do you optimize the energy? There is this agent takes certain actions, and based on that actions, certain things happen over here that actually optimizes the energy. And based on that one, it actually receives different state and then the reward itself. And then this agent is learning based on that one, based on the action that it takes. This is another example. Why I included this example is it will be easy for me to explain What are the things that, like for example, I'm talking about action, I'm talking about reward, right? I'm talking about environment. What are these things actually? Because these are the, as I already mentioned, these are the fundamental things of reinforcement learning. Now let me explain you this figure in detail. If you look at this figure, this is the board. You can consider this as a chessboard, you can consider this as a, kind of go board here, or you can consider this as a maze as well, maze. So the objective is, the agent is somewhere over, the target is somewhere over, the agent or starting point is somewhere over, the agent has to move to all these cells over here, and it has to reach to this target, let's say. So it has to follow certain path to reach out over there. So the action for this one, the agent, probably this is the agent, let's assume that this is the agent. So agent can move at any instance. The agent can either move up or move right or move left, or it can move down. So there are 4 possible actions, and these are the actions that we consider usually. But it depends on the context as well. If you are talking about smart grid or something else, then the set of actions might be different. But in this example, any agent has to move from this part to this part. You see, the agent is already over here. Agent can take 4 different actions. So this is the set of actions here. So the agent takes certain action, and if this agent does not reach to the target, probably it will get a very less value as a reward. This is the environment actually. Every moment at any given time t is the state or the status of this environment. That is the state. So state, this environment actually provides state information of the state to this agent, and based on this state, the agent takes certain action. And how does it actually learn is, there are so many other mathematical calculations. I'm going to talk about that one. But right now, what I'm trying to explain is what is actually state, state, and what is actually reward, what is actually the action. The set of actions here, as I mentioned, are only 4 at this moment. Up, right, down, and then left, and then it provides the reward as well. Reward is basically, if the agent is over here and it tries to move right over here, probably it gets only value 1. So that is a numerical value. So that numerical value is actually considered as a reward in our programming context, let's say. Or if somehow when agent moves forward, and then if it reaches to this target, let's say, from here in this location or from this location, if it reaches to the target, probably it will get 100, because 100 is greater than 1. And the agent understands, okay, so if I reach to that particular cell, and that is the target. Because initially it doesn't know that is the target, but when it receives 100 reward, 100 value as a reward, then the agent understands, okay, this is where I have to reach. And that reward actually, the reward that it receives from the environment actually informs the agent that, it is informing the agent that you are supposed to reach to that particular cell, right? So that is how the agent actually is learning in this case. So this has to go on and on, so multiple times, and finally the agent understands that, okay, from anywhere in the board over here or somewhere over here, it has to reach to this point because I'm going to get the maximum reward. So what is the ultimate goal of agent is, the ultimate goal of agent in any context here, whether you are talking about smart grid or whether you are talking about AlphaGo or whether you are talking about LLM, the human feedback, or whether you are talking about Atari games, the ultimate goal of agent is to maximize the reward. Maximize the reward means what? Whenever it has to take any action, that action actually returns certain value. That is what we call reward, and the agent has to maximize that reward in every moment. And there comes the whole, the scenario, the picture of reinforcement learning. Now, let me give you one more example. This is actually the application of RL in the field of autonomous vehicle, and Professor Ronak is there to explain you more about this one. He will talk more about like how autonomous vehicle is going to utilize reinforcement learning algorithms. So here I'm to explain what reinforcement learning is, and Professor Ronak will explain how to use that one. Let me give you one more example. Why I included this one is this was actually a part of my PhD, where I actually used reinforcement learning to optimize the inventory management, inventory optimization. I applied reinforcement learning in the inventory optimization. So here in this example, so if you look at this agent is not only an algorithm, but it actually uses deep learning as well. This is why we call it deep reinforcement learning, not only RL, but deep reinforcement learning. This agent has to take certain actions here, and then the inventory has to be fulfilled. Like for example, let's say the agent decides on how much to order from the distributor so that I can fulfill all the demand from the customer. Let me assume that if I am the seller, let's say, if I am the retailer, if I am selling something, some product, let's say for example beer or whatever, there is this beer game problem in management, in supply chain management, and it has been solved by RL wonderfully. It has been solved by RL as well. So that's why I'm taking this example. Otherwise, please do not take it otherwise, okay? So if I'm selling beer to the seller has to, keep the stock of beers in my, for example, yeah, I'm the seller, I have to stock the beer in my inventory, right? But then how much shall I order from the distributor so that I can fulfill all the demands from the buyer, you see? So that I have to decide as a seller. And here in this example, this agent is a seller, and agent decides how much to order from the distributor, and all these things happen, and every time it takes certain action, it provides me the reward, and based on that reward, okay, so this is the amount that I need to order. It understands that one, and then it takes certain action. So this is a very simple, diagrammatic representation of optimizing the inventory problem using reinforcement learning. We can talk about this one more. Let me take one more example. It's a very popular example. Whenever we talk about reinforcement learning, or whenever I'm supposed to teach, what RL is, I usually take this example. This is a cart pull problem. So in this problem, now the way I take this example is to explain you again what are the state, what are the actions, what are the rewards. So in this problem, if you look at this one, this is the pole, and this is a cart. So cart has these wheels over here, and cart actually move back and forth here. You see, you put some force over here, and it moves on this side, on the right side, and then the pole also, tilt on left or right, depending on the force, right? Depending on the movement of this cart. And the objective is, what is the objective? Objective is to balance a pole on top of the movable cart. This is the movable cart. It moves left and right, and this port has to be balanced. You see, that is the main objective. Now in this example, how are we going to use reinforcement learning? So to implement this reinforcement learning, to solve this problem using reinforcement learning, what you have to do is you have to talk about this state. You have to talk about the action, and you have to talk about the reward. You see? So now what is the action? What is the state here? State is the angle, angular speed, position, and the horizontal velocity of this pole. You see, because it tilts either on the right side, it tilts either on the left side. All these information actually form a state of this problem. You see? And what is the action that we can take? It is the horizontal force applied on the cart, whether it moves on the right, whether it moves on the left, that is the action. So in this example, in this problem, the set of actions contain only two things. You put the force on the left, or you put force on the right. So it only has the force, on the right side or on the left side. That are the two actions for this problem. And what is the reward? So every time it balances, you can get 1. If you don't balance, it can get 0. You see, or you can define by yourself. Like for example, if it balances well, you can get reward can be 10, or if it doesn't balance, the reward can be 0. It depends on what the number you use. But then this is again, let me tell you frankly, this is again a very serious problem. That's why in the reinforcement learning, we have a different research field. We call it reward shaping. How do you actually define a reward? You know why this is very important? Because if you do not define the reward equation properly, the agent will not learn properly. So this is why the reward shaping is very, very important. The equation that you define as a reward function is very, very crucial, because the agent learn from the reward based on that one, based on the reward. So let me give you one more example. This robot locomotion. It's again a fantastic application of reinforcement learning, where the objective of this robot actually is to make the robot move forward. So the robot has to move forward. I mean, like walking. The robot has to walk. So that is the objective. But then how do we make it happen using the reinforcement learning? Again, what you do to solve this problem is you define the state, you define the action, and then you define the reward. If the robot moves, then you get reward 1. If it doesn't move, if it falls down, then you get 0. You see, that is the reward. And what is the action? Action is the torque that you applied to this robot, because torque has to be there to move forward, right? So that is the action. And what is the state? Angle and the position of joints. There are so many joints over here, basically the leg joints. So joints and all those stuffs are basically the state. So based on this action, the robot can move forward, and it can fall down again. But if it fell down with that particular action, then you are going to get 0 as a reward. So the agent receives all this reward based on the action, and it learns how to move forward. This is one of the best examples of reinforcement learning. Like I already mentioned, Atari game was again another game where RL was used. In this game also, how do you solve this problem? Basically is you define the object, state, action, and then the reward. I'm not going to move this, I'm not going to talk this one in detail. Let me move another example. Here in this example of Go, what is the main objective of Go? If the agent is there, if the machine is there to learn, and finally it has to win. That is the goal of this this game. So how do you solve this one? Again, using reinforcement learning is you define the state, you define the action, and you define the reward. So state basically is the position of all pieces. So there are so many pieces, black and white pieces are there, you see. So this can be one state, one of the millions and millions of state, right? It has million state, because if you remove this piece, let's say, then that can be another state. So there are so many, states of this game Go. That's why, so when RL actually won this game, that's why a lot of people appreciated that RL has won, because there were so many states. If you compare this game with chess is nothing in front of this AlphaGo, this game actually. So this AlphaGo has much more states compared to that chess. And what is the action here? Where to put the next piece down. For example, if it is the black tone, then the black has to be the black piece has to be placed somewhere, right? And that is the action basically. For the white, it has to put that white piece somewhere, and that is actually the action. What is the reward? 1 if it wins, otherwise 0 otherwise, right? So this is how you actually define. It looks pretty simple, but then when you actually implement it, it's quite challenging, very, very challenging. RL has so many serious problems actually. I'm going to talk about that one later in the slide. I have included those things, and then you can explore more on those parts for the future research. So let me now talk about what is Markov decision processes. I already mentioned like what sort of applications of RL are there in the society. You know, what real problems can be solved using RL. But every time I talked about RL just now, I mentioned three things: state, action, and then reward. If you are, let's say, mathematically trying to represent, you are trying to represent the problem mathematically, then you have to represent that problem in the form of MDP, Markov decision processes. So there is this property called Markov property. Please go, you can look into that Markov property later on. What is Markov property? Because of the Markov property, you know, Markov process, MDP is useful in RL problem, in solving the RL problem. So what is the mathematics behind this one? It is actually a tuple. Sometimes you see only 4 tuples in this representation. Sometimes you have like 5 tuples in components there. What is S? S is actually the set of possible states, like I explained you, right? In every problem we have state. So if you can define that set of problems, and that is one component of MDP. Another A actually stands for set of possible actions. For example, you remember in one of the games there, in the board games, the agent has to move from one place to another, and you have like 4 actions that agent can take. One is up, the other one is down, left and right. This is actually a set of actions, and we represent this as A. So here, this A. What is R? R is the distribution of reward. You have to define the reward equation. Then only RL agent can learn something from particular action. What is pre? It is the transition probability. So what actually this probability is? What is the probability is doing in this RL actually? Now, I already mentioned that whenever you consider any problem, right? Any problem, there are so many states. Now let me assume that you are in the state S1. State S1. And you can go to multiple states, let's say S2, S3, and then S4. Let me simplify this one. You can move from state S1 to only S2 or S3 or S4. So moving from S1 state to S2 state might have certain probability, probably 0.2 probability. There might be a case where moving from S1 to moving to S2 might have 0.5 probability. So if you have that kind of context, if you have that kind of problem, you can actually describe or you can explain that there is a probability from moving this state to another state, and that is what we this transition probability is represented. All those probabilities are represented by this symbol P, probability. And this another component in the MDP is what we call discounted factor. It's a fantastic, invention, I believe. Discounted factor, I'll talk about this later on a little bit because it is actually embedded even in the Bellman equations. Discount factor actually is, I have forgot one thing. Let me tell you. Reinforcement learning is useful in those problems that actually has kind of, problem related to sequential decision making problems. Sequential decision making problems means I am not right now interested in the immediate reward. I am interested in maximizing the reward at the end. Because to win the game, I have to take so many actions. One action at a time. So I take one action, I get the reward. That action actually puts the environment into different state. I'm going to take another action based on that state again, based on that state and the reward. I'm going to take another action, and it again gives me back a certain reward. So these things happen, and this is what we call sequential decision making. because I'm making certain action each and every time. After t, at time t, let's say, at time t, I take certain action. At time t plus 1, I take another action. At time t plus 2, I take another action. So at the end, what is my goal? I want to win at the end, not at this moment time, probably time t. You see? So this is a sequence of making decisions. If you see a problem in this sequential form, in this sequential decision making form, then you can be pretty sure that, okay, I can make use of RL to solve this problem. I can make use of this RL to optimize the problem. You see? So even if you look at the inventory problem, that's what we usually do. I have to take certain actions. Probably I have to order certain inventory, not only at one single day, but I have to make it multiple in every day to maximize my profit. You see? That's where the RL plays a very crucial role. So now the point why I'm explaining this part is, so the reward that I get immediately, the reward from the environment that I get immediately may not be useful, 100% useful, may not be 100% useful, because after a certain time, I'm going to take another action and I'm going to get another reward, right? So the goal is to maximize, if my goal is to maximize the reward in every moment, you see, in every moment, what I have to do, I have to accumulate all those rewards and then see if those set of actions, if that sequence of actions actually get me to maximize the reward or not. So that is the main point. Now the question is, the reward I get at this moment and the reward I get after a certain time, even if I get one at this time and even if I get one after a certain time, they look equal, 1, 1, but in fact they are not equal. Let me give you one example. Everybody gives this example basically to understand this discount factor. For example, if you have $1 at this moment, you see, $1 at this moment, and after 10 years, if you have got the same amount of money, like $1, are they equal in value? No, they are not equal. So this exactly happens, same thing happens in RL as well. The reward I get at this moment is more valuable than the reward I get probably after a certain time. So how do you integrate this philosophy in RL is by introducing discount factor. What we do, very simple algorithm, this is very simple concept. What we do, at this moment, what I get, for example, if I get reward 1, that's fine. At this moment, 1 is equal to 1. But after a certain time, that 1 is degraded by certain value. You see, we make that 1 probably 0.9 or something like that, or 0.95. So we reduce that value. So the reward that we get at the end probably is not same as the one that I get right at this moment. So that is what we call discount factor, and this is very, very crucial. Even if in Bellman equations we see that discount factor, but how much do we with how much amount we actually reduce? Probably 0.005. With that value we reduce the reward. So that is actually discount factor. If you able to explain all those 5 components based on the problem, that's what I did actually. I look at the inventory problem, and then what I did, I wanted to solve this problem because this is a sequential problem. Then I immediately thought that, okay, this can be solved using reinforcement learning. And then what I did, I actually study the problem very clearly. And then everything was clear to me with a limit. Definitely there are certain assumptions actually. So what I did, I convert that problem into MDP first. Before I using RL, I converted that problem, inventory problem, into MDP. How do I did that? How did I do that? I defined the state, so these are the states. I defined the actions, so these are the actions. It was very simple in inventory over problem as well. I defined the reward as well, reward function. Reward function is actually, how did I define that? It was based on the cost, I think. The cost, there is this cost called shortage cost, and then holding cost were there. So I used those costs to define the reward, and I defined the discount factor, but then there was no transition probability. Because in that problem, we didn't know what is the probability from one state to another state, moving from one state to another state. So what I did, if there is no transition probability, then still we can use RL, of course. But then I came to know that there are two types of RLs based on these probabilities. One, what we call model algorithm, model, where you have all those probabilities, transition probabilities are all defined there in the model algorithms. But there is another we call model-free algorithms. So in model-free algorithms, you do not have to specify the transition probability. It is all free. The agent, the state can be in S1 and it can go with S2 with, we don't know the probability of that, transition. So to solve this problem, that's why I used model-free algorithms, and Q-learning is one of them. Q-learning is one of the model-free algorithms, if you are familiar with that one. Now, let me quickly move into this very common, MDP problem, grid problem. So if you look at this problem, let me explain you what this problem is. So we have, this matrix, this grid, 3 rows and then 4 columns, and this is a place where you are not allowed to enter. Okay, the agent cannot, or the robot cannot move. You can suppose that the agent can be in this place, or agent can be somewhere over here, agent can be somewhere over. This might be the destination over there, destination. In this case, in this example, if this is the problem, let's say, what you do, you define the actions, or you define the state first. The state is basically whole. The image that you see actually is the state itself. And what could be the action? If you assume that the robot is somewhere over here, the agent is somewhere over there, the agent can move right, the agent can left, up and down. These 4, again, are the actions, set of actions. So you define that one in the programming or in the problem itself. And what is the reward? Reward can be negative. If you do not reach to every step that you take, every action that you take, if it does not take you to the destination on the top right, left, right corner there, top right corner, if it doesn't take you to that place, probably you're going to get negative, -1. If you reach over there somehow, that will actually give you probably 10 reward. But then how does this actually happen? But before moving to that particular problem, to understand how does it actually happen, getting reward, and finally it is learning, the agent actually learns to reach to that destination. How does all these things happen? Defining state, defining actions, defining reward equations, is not sufficient. You need to understand the very core concept of reinforcement learning, and those are what we call value functions. Value function. I'm gonna explain this one right after this diagram. Let me show you this diagram first. Okay, so if the agent has to move from one point to another point, it can go to any direction, right? Up, down, left, right, anywhere, agent. And that is what we call a random policy. If it has to go to somewhere else, some in other cell, then it can take any direction. But that is a policy, of course that is a policy, but it is a random policy. And it does not guarantee the optimal way. That is the optimal path. It does not guarantee. It does not guarantee that it will reach to that particular destination as well. But then if you look at the optimal policy, what is the optimal policy then? The optimal policy looks something like that on the right side. If you look at the right diagram, the optimal policy probably look like that. Somewhere in the cell, the agent is there. If you consider agent in any of the cell there, then it can take in many directions. For example, if you look at the last row and then the first cell over there, it can go up, right? It can move to another one, and it can move. It can take different actions there as well, but with the probability. Why it doesn't have the right side? Because right direction, moving to right from that cell, will probably not lead to the optimal solution. So the reason why agent actually, when trying to learn something, when the agent, why agent is actually learning, agent is actually maximizing the reward, is to have the optimal policy. Once the agent maximizes the reward, agent learns something, then we say that agent now has optimal policy. What is policy basically? Policy is something that you do, based on the reward. Policy is something that you do, that you take certain actions, sequence of actions, and that actually leads to the optimal solution. That is optimal policy. You got it? That is optimal policy. But to understand the optimal policy, to learn the optimal policy, RL takes so long time. So you have so many episodes, running, and then RL agent has to learn so many different states and so many rewards. It has to receive to reach to the optimal policy, to get to the optimal policy. It's quite challenging. It's very compute hungry, in fact. Now let me go to the core concept. Like I said, defining a state, defining a set of actions, defining a reward function may not be sufficient for you. You need to understand the core concept. So in the core concept, we have value functions. There are so many other things. Probably Professor Ronak will explain you more on that part. But then this value function is one of the core components of reinforcement learning. What is actually value function? So value function can be divided into two parts. One, we call it state value function. Okay, state value function. The other one is action value function. So state value function actually gives you a value, certain value. I'll tell you what is value actually. What does value that represent? What actually that value represents? An action value function also gives you a certain value. Okay, certain value. But what does it represent then? What does it tell you? The value actually tells you, this value function gives you a value, in fact, and we need to define that one. And that is the equation that you see over there is actually a value function. So the value function actually returns a value that tells you how good, how good the current state actually is. Right now, for example, like I explained you what are the states, right? So you will be in one particular state at any given time t. You see, a little bit into the mathematics now. So imagine there is this state, only one state. Agent is somewhere in the grid. Let me take you that example, grid example, okay? Grid problem. So the agent actually is somewhere in the grid, in the cell there. But then it has certain value. That means how good that state, to be in that state, is actually. Good in terms of what? Good in terms of that to maximize the reward, to get that optimal policy, to get into the destination, how good that state is. So that is actually defined by the state value function. So this equation actually the state value function. So it tells you that if there is this certain state, the environment actually defines the state, and this value actually gives you the value. The value function actually gives you the value that defines how good you are in that particular state. But there is another kind of value as well, and that is what we call action value function. So the action value is actually, you have to define there, because you also want to know that how good the action in that particular state, if you take that certain action, how good that action is. Because ultimately we are trying to maximize the reward. You see, we are trying to maximize the reward. But to maximize the reward, you need to understand how good, in a state you are, right? How good the action at that particular state is. So these are the two different values. So if you are talking about the value at that particular state, then this equation is useful. If you are talking about the quality of the action or the value of the action, how good that value is, the action is, then we need to define another parameter, but with the similar kind of equations. So here, if you look at this one, V equals to expected reward. So if you look at this, there is this discount factor, right? So discount factor and then the reward. And then this is the initial, SO is the initial state. SY, there is this another state, ST, I mean next state, right? Pi is the policy. So moving from one state to another state, and what is the expected reward that you get actually is the value itself. You see? So based on this kind of values, the agent understand that, okay, if I take certain action, you see, you got my point. If I take certain action, and if the state is something else, how good that state is, it understands this everything, this part, these things, these steps, by using all these equations. And at the end, it actually maximizes this value. So once you maximize this value, then the agent, we say that the agent is actually has now optimal policy. Now let me move to another equation. This equation actually is very similar to the previous equation. There's a value function, and this one is actually action value function. So this is again, you see the Q symbol over there. That actually represents the action value function, action value. How good that action is actually in that particular state. Because the action that you take, the same action that you take might be in the different state, you know. In one state, you take the same action, A1, and in a different state, you can take the same action, A1, but in the different state, and it takes you to the different actions. So if you look at all these pictures into one pictures, you can have, a very huge number of states. Big number of states are there, a lot. And that's why the human capacity is limited in that part. Whereas this RL actually goes through, in every state, and it calculates those values. It identifies whether, okay, this state is not good. It identifies, this state is really good, because it maximizes the reward, you see. So how actually RL agent is learning is by calculating all these values. And these values actually help an agent to maximize the reward. So maximizing the reward actually means, so you are in the right direction. You are in the, optimizing the policy. So that's the point. Now let me talk a little bit about rewards, as I already explained. 10:30 सम्म यो चाहिँ मलाई, thank you. Okay, so reward actually, let me skip this slide because I already explained. Reward can be, basically it's a numerical value, scalar value, right? So it can be 1, it can be 10, it can be, but how do you define the reward in your programming? Basically in your problem formulation is, let me weigh this one. Now I am officially a presenter. Okay, thank you. So how do you define this reward function is basically, if the state is good, or if the action is good, or if that actually maximize, gives a very, values are good, then actually reward is, you get the better reward. For example, let me take you the inventory management problem. Okay, let me quickly explain. How do you define the reward? Because this is very, very important. So let's suppose I am a seller. I want to sell beer to all the customers. I have the stock over here. I take certain actions. That is, I ask the distributor, please send me this many bottles of beers. So I keep that in the stock. If that many bottles of beer actually fulfill all the demands of the customers, then I'm going to get good rewards. So how do I define that reward? Is basically reward equals to the profit that I make each day. You see, that's how I define the reward. But in different context, it's different. For example, in energy problem, how do you define the reward? Reward is basically the profit that you make when saving the energy. While saving the energy, you have certain profit. That is actually, if you sum them up, that is actually the reward itself. So it is nothing more than, more than the equation basically. It gives you the scalar value. But then again, to define that equation, you need to understand the problem very, very clearly. If you fail to understand the problem, you fail to define the reward equation. If you fail to define the reward equation, the agent will fail to learn. So that's a very, very important part. So let me quickly move to the next slide. So this is the cumulative reward, because in every step, if you look at this one, Rt plus 1 is the reward at time t plus 1, Rt plus 2 is the reward that I get in the next action, but then there is this gamma symbol over there, that is the discount factor. But that reward, why we do not take reward Rt plus 2 as it is, because we get that reward after a certain time and it has to be discounted. And that gamma is actually a discount factor, probably 0.001 or something like that. So, and if you sum them up, because at the end we have to maximize the reward, right? Not at particular moment. We have to maximize the reward at the end of the game or at the problem. So that's why we sum them up, and GT actually represents the cumulative reward. So from these equations, we define the Bellman equation. The Bellman equation actually comes from value functions. It comes from action value functions, it comes from those rewards. It comes from the discount factor that you define, you see. So this is a very fundamental thing of reinforcement learning. This is how actually you calculate the value, and with this value, you actually maximize the reward. With these equations, you actually move into, the optimal policy. Now this is the Bellman equations, and it is derived from all those value functions. And I have skipped the derivation functions actually. So now let me move to a very critical part of reinforcement learning. I still have a few more minutes, 10 to 15 more minutes. What is exploration and exploitation? Now imagine that there is this RL agent. Let me consider this as a RL agent, okay? It has to learn something, right? It has to learn something. In RL, the environment initially is actually unknown, because this RL agent doesn't know what to do, which action is good, right? Which state is good. It doesn't know that one at all. So what it has to do is it has to explore. Okay, probably this action, the action that I take, for example, moving up might lead to maximum reward. It assumes that one and it does that, right? But it may not lead to the maximum reward actually. So what it does actually is sometimes it move up, sometimes it move right, sometimes it move left. You see why it does that one? Why do we need to do that one? Is because we do not know initially. We do not know what action actually gives a good reward. So we try to explore many things. For example, for an instance, if you are going to some new place and you have to go for dinner or lunch, what you do? You actually explore, right? You try to go to one restaurant, you eat there. If it's not good, you move to another restaurant and you get better one, right? So to get the better one, to know the other action is good, it has to explore. But then always exploring may not be a good idea. You know why? Because it wastes your energy. If the agent only explore every time it explore, it may not reach to the optimal solution, but then it always wastes the energy. You are just exploring. So what is the another option? The another option is to exploit it. What is exploitation then? Exploitation is, for example, again I take the same example. You are going to some new place and you tried one restaurant, for example. Probably three restaurants or 5 restaurants, and you know that one particular restaurant provides a very good meal to you. Then what you do, you most of the time you reach to that restaurant for the meal. You got my idea? And that is what we call exploitation. You know the action is good, but you do not know that action is better than the other one. That's why you need exploration as well. But then if you already know that it is really good, then you try to act with that action. You try to choose that particular action, and that is what we call exploitation. So exploration and exploitation is why it is critical, is because all the time exploiting may not lead to optimal solution again. All the time exploring is also a waste of energy. So the question is, how do you solve this one then? Then we balance it. We exploit also, we explore also. We balance it. And balancing actually is very challenging. And there are certain algorithms like epsilon greedy algorithm, Thompson sampling algorithms, These are some of the algorithms that actually, manage this dilemma, this trade-off. That's why this exploration and exploitation is a very critical point. And even now, if you talk about DQN algorithm, if you talk about PPO algorithm, GPRO algorithm, all these algorithms, they actually follow this exploitation and exploration concept, and they try to balance this one. So let me quickly move into now another. These are some of the examples, real world examples, basically where you apply exploitation and exploration. But then again, I want to skip this slide as well. Now let me move. Now what we understood so far is, let me revisit, okay, whatever I taught. We saw the applications of RL, different fields where RL can be used. We understood how RL can be transformed into mathematical representation. We call it MDP, right? We understood MDP as well. We understood state, we understood actions, and we understood reward as well. And then recently, right now, I also explained how exploitation and exploration play a very crucial role in reinforcement learning, you see. And I also talked about the value functions as well. Those are the functions that actually help us to maximize the reward, right? You need to calculate those values. So combining all these things, we have this algorithm so-called Q learning. It is very, very popular. The inventor of this algorithm is, I think, Christopher Watkins, I think. This Christopher Watkins is a scientist, researcher. He actually developed this algorithm called Q learning algorithm, and it has been popular since then. Probably in 1990s, he invented this algorithm, actually. He discovered this, developed this algorithm. This algorithm is off-policy algorithm, means that agent actually learns something, it learns something with certain policy, but then it also tries to explore another policy. And if another new policy is better than the policy that it is using, it adapts with the another policy. It explores, it tries to maximize the reward, with the new policies. And if new policy, every time if new policy is better than the old policy, then it adapts with that new policy. That is why we call it off-policy algorithm. And this is a fantastic algorithm, actually. And this equation is what we call Bellman equation again. And you see the last two terms, QS1, S prime, A prime minus QS, comma A. S is the set of state, of course, any state, any particular state. A is the action. So that two parameters actually form the temporal difference in RL. Temporal difference is again a very crucial factor in reinforcement learning. How does any robot actually learn to do something, or agent learn to do something, is basically based on the temporal difference. We call it trial and error. You see, we try, we get error, and we improve our policy. That's how RL actually works, right? So this temporal difference is actually embedded in the Bellman equation itself, and that particular equation actually is exploited by this Q learning algorithm. That's why this Q learning algorithm we consider is one of the best algorithms in reinforcement learning. Now let me come to the end of this presentation. Let me just introduce deep reinforcement learning, okay? So what is deep reinforcement learning is, when we talk about Q learning, most of the time we talk about tabular. I mentioned that we have these Q values, right? We need to calculate Q values because we need to know how good the action is, right? So we calculate values and we keep those values in a tabular form. Let's say matrix. We keep those values in the tabular form in traditional way. This is what we call tabular Q learning method. But then what happens is if the state of your problem is huge, if the states are huge, if the actions are very huge in numbers, then tabular form actually is useless. It cannot handle all those dimensions. So if your problem, when you define the problem and the state and the actions are huge in number, I think you have heard about course of dimensionality, you know? If there is this problem this course of dimension in your problem, then this way of solving the problem, keeping all those Q values, calculate the Q values, you store those Q values in the tabular form is not a good way. So what we usually do, we remove those tabular form, table, and we replace that table by neural network. So what does neural network do? Neural network does not store all those Q values. It approximates the Q values every time. That's how this deep learning is being used in reinforcement learning. So when you use this concept, you see, this concept, then we call it deep reinforcement learning. So now what I'm trying to explain you, what I'm trying to tell you is that we have this agent, we have this environment, you see, they communicate with each other. We know Q learning algorithm, right? So in Q learning, in tabular form, what we have is we calculate Q values. We need to calculate them because we need to understand how good the state is, how good the action is. So we calculate all those values and store in the tabular form. But this is not good enough because of the huge number of dimensions. So we actually, what we do, we remove that table itself and we replace that table with neural network. Why we replace this with neural network? Because neural networks are good in approximation. So how does it work? We train that neural network to approximate the Q values so that we do not have to store all the Q values right over there. You got my point? So this introducing this neural network in the agent itself is a great idea. That's when these Atari games where, this Atari article, there was this article explaining all those Atari games, right? How this deep neural network, deep reinforcement learning actually played good, Atari games. So we replace that agent with the neural network, and now we call this framework a deep reinforcement learning. In deep reinforcement learning, now what we have is different algorithm, and one of the most popular algorithm, the initial algorithm, was deep Q network. In deep Q network, we have this kind of structure. You see, this kind of structure. So if you look at the neural network, if you look at the deep Q network itself, you will see two networks over there. One is called Q network. The other one is called target network. You see, the target network and the Q network. We train them from the experiences. Now, what is experiences? You remember when we talked about MDP, we have those tuples there, S, A, you remember that, transition and all those things. So if you have that set of information, we can store that in a particular buffer within that DQN framework. And that is what we call an experience. For example, let me give you an example. In any particular state, we take action A1. With that action, we receive reward R1, and it moves to the another state S2, let's say. S1, moving from S1 to S2 with the action A1 and the reward R1. There are 4 tuples, right? 4 information. If you combine them into one tuple, and if you store this information in one of the buffers over there, in the buffer, that is what we consider as an experience. So with that experience, all these neural networks actually learn which state is good, which value, and then it tries to calculate, it tries to approximate the Q value. You see, I'm not going to talk in depth, but then when you look at this structure, there are multiple things. One, you came up with the idea that there are two neural networks, not only one, two neural networks. One, you train, you get the good Q values, it approximates the Q values, and you copy that one, weight and biases basically, you copy that things into the Q network. And it actually approximates the Q or action actually. And we have this buffer over here. We store all those experiences. What are experiences again? Experience is a tuple, nothing more than that. State S1 to S2 with the action A1 and with the reward R1. So with all these experiences, neural networks are well trained with all those experiences. But then again, there are so many problems by introducing this buffer itself, and we have this so-called priority replay buffer. We prioritize, we randomize, because there are certain problems. If you take the set of experiences, consecutive experiences, it may lead to the suboptimal solution. So what we do usually is we take random experiences from the buffer. So there are so many experiences collected, so we randomly pick from different instances, and that actually helps to generalize the learning actually. So there are so many things you can study within the deep Q network itself or deep reinforcement learning. So DQN is one of the most popular algorithms. There are PPO algorithms, there are so many other stuffs, but I have to complete by 10:30. I have 6 more minutes. So I quickly go into another slide. If you have any problem, we can discuss that later on. I also wanted to talk a little bit about this optimization, inventory optimization problem, because I worked a lot in this field, but then let me skip all these stuffs. There is beer game problem, there is this. So if you look at even in the optimization, inventory optimization problem, there are different fields, particularly in the supply chain management itself. For example, retail, manufacturing, pharmaceutical, there are so many, problems out there that can be solved using reinforcement learning. Now let me repeat once again, why do you want to introduce reinforcement learning? Why do you want to solve that problem using reinforcement learning is because when you realize that it is actually a sequential decision making problem, then you try to solve that using reinforcement learning. But then again, there are certain challenges. With this slide, I'm going to conclude my presentation. There are certain key challenges. One is high dimensionality state action spaces. Like I mentioned, course of dimensionality, So if you have like huge number of dimensions, it's quite challenging for RL or DRL to solve. And non-stationary demand, this is the one that I actually consider, I consider inventory optimization problem, so I included this one. And reward shaping is again another, like I mentioned, because I already mentioned that why reward shaping is very important. But then the key challenge is that there is this sparse reward, reward values. So how do you, holistically actually look into the reward is very, very important. You have different values of reward in the dimension, sparse way, but then how does RL actually consider that value? How does certain value actually is being represented is a very challenging part. So reward shaping is again another field, RL, and this is always another. This sample efficiency is another always. It's a big challenge for not only for RL but for machine learning itself as well, or deep learning itself as well. So these are some of the fields that you can explore. Explore more actually. But then let me show you some of the great actually scientists who work in RL, and right now RL is basically in a great shape, and these are some of the contributors. If you remember him, Richard Southern, he is still active, he's a professor, he's a wonderful guy, Sergey, and then David Silver, John, PPO, he's the last one who actually developed PPO algorithm. PPO algorithm, it's a great algorithm with a big efficiency. And let me show you this textbook, Reinforcement Learning, written by Richard Sutton and Mark, what do you call it? Bartho. So this book is actually a textbook, and every time when I teach my students about this RL, I consider this book as a Bible of RL. So with this one, let me conclude my presentation. Thank you so much. Thank you so much for your patience, and then I hope you got some idea about reinforcement learning. It's all the foundations of learning. I mean, in the next session, probably you're gonna learn more about this deep reinforcement learning, and then the real application of RL. So let me quickly take a couple of questions. If you have any questions, please raise your hand, and then you can ask. Mike, actually, Mike, दिन सकिन्छ होला उहाँहरूलाई? अब चाहिँ लाइट अन गर्न सकिन्छ कि जस्तो लाग्छ? You can tell your name, where are you from, right? What your research area, and what is the question?
My name is Shakya, and I'm currently studying electronics and communication information engineering in Nepal campus.
Okay.
And so I was thank you for the lecture first of all. And so in exploration versus exploitation, you said sometimes too much exploitation can also lead to non-optimal solutions. So basically, I understood exploitation means gathering as much reward as possible. Am I correct on this part?
Exploration, you mean? Exploration?
Exploitation.
Yeah. Okay.
So am I correct here? Exploitation means the agent tries to gather as much reward as possible.
No, that is exploration. Let me tell you. Exploitation is you already know the values, right? And you think that that is really good for this particular state. That action is really good. So you always try to select that particular action because it is really good in that particular moment, whatever the values you have. So exploration is, although you know the particular action is really good, looking good, but you try to take another action to see whether that action will be better than this one or not. So that is exploration.
So my question was, how does exploitation lead to sometimes non-optimal solutions?
How does exploitation?
Yeah.
Okay, good question. Thank you very much. How does it actually lead to the suboptimal solution? So what happens is, first let me address this question, okay? So if you do not perform the exploration, if you do not perform the exploration, you do not know that there exists another action for the same state that is better than the one that you have. You will not be aware about this particular action, you see, this particular action, because you consider one state, for example. In this state, what you know is action A1, let's say. A1 is the action that is good for this particular state. You only know that one. But unless and until you do not explore, you will not be aware that there is another action A2 in that particular state, in that particular same state. Action A2 is useful or better than the action A1 in that particular state. So the possibility is that A2, there is another action A2 that is useful, that will lead you to the optimal solution, probably better than the action 1. That's why exploration is very, very crucial in that part. Thank you very much. It's a very important question, in fact. Let me take another question. I think, Bani, I mean, दुईटा question लिन सक्छौ, अर्को एउटा? Okay. Oh, sorry. Let's take.
My name is Krishnan and I'm currently working as RA at NAMI, and I have a few questions. In some situations, like a game of chess, sometimes not all the actions are legal. So how do you model? Does that modeling fall under Markov process or not?
Thank you. Very good questions. What happens is, I also actually wanted to talk about this one, but we can talk that later on, right? But give you a very short answer. What happens is, you have this agent, right? RL agent. So the RL agent can take, like, let's say 4 actions, up, down, right, and left. Now there might be different states where all those 4 actions are not possible at all. only one action might be possible. For example, you can only move to up or right. Two actions are possible. So in this case, my solution is, I think it is better to implement what we call action masking. What you do is, if you are in that particular state where only two actions are possible, only two actions possible, then other two actions, what you do, you mask them, so that the agent itself, RL agent, does not actually take that action at all. And that's what I also explored in my PhD, during my PhD. Yeah, thank you very much.
My another question is, in some games, many multiplayer games, there are multiple agents. So, is there something in IRL where there is supposed to be a cooperation or some sort of messaging without explicit communication?
It's again a very good question. In fact, I have not worked on multi-agent reinforcement learning, and now it is getting really popular, because why we need multi-agent reinforcement learning is because in any game you consider, for example, football or cricket, right? So there are multiple agents. Different agents actually take different actions, right? So that's why we need multi-agent reinforcement learning. But then I have no idea actually how they communicate. But there must be some kind of communications, because their goal is actually to win a game, right? Or maximize the reward. So one agent has to communicate with another agent. But then there are certain contexts, there are certain problems, there might exist certain problems where each individual agent actually perform independently without any cooperation. But then if there is a game, or if there is a problem with the common goal, there is a common single goal. For example, in football, 11 people. 11 people. So 11 people, working together to win the game. So in that case, if you apply multi-agent reinforcement learning, in that case probably you need to communicate with each and every one. So I think communicating is basically a message passing system. That's what I know. But I have not really worked on multi-agent reinforcement learning. Thank you.
My another question is, can you clarify in short about what the target network actually does in deep learning?
Okay. So what happens is, now let me explain you. Suppose this is Q network, right? Q network is right over here. And suppose there is this another, what we call target network, right? We have target network. So one network, how do we train actually is by using the experiences that we store in the buffer itself. In the DQN, if you look at the DQN framework, there is this buffer system. In the buffer system, buffer is nothing more than the storage, simply array, let's say. So in that buffer, we have all experiences over here. So with this set of experiences, we train one network, and it actually learns from all these experiences. And now, once it learns, it actually transfers that information to this Q network. Now this Q network has an up-to-date information. Now, what happens is, when the environment, when it takes certain action, let's say, the environment changes, the state changes, right? So it gets all the informations. Now, how does this actually Q network works is basically with all those different state again, it actually takes the state information as an input, and it actually gives you different Q values. And with that, every Q value, there is a corresponding action. You got my point? For example, certain Q value, certain action, certain Q value, another action, another Q value. So among all these Q values, the maximum Q value, what is the corresponding action of the maximum Q value? It actually executes that particular action. You got my point? But then it has to approximate all the Q values, right? But how does this neural network does that one is basically with the help of another one. Why we need the help of this one? Because it It has learned from all the experiences. Right? This is how they are connected to each other. And I think this is again the Bellman equations that it is implemented in this scenario as well. I hope I addressed your answer, right?
I'm still unclear about what are the input to the diagram method and what it actually outputs.
Oh, okay. So it's all like Q values only. So the output is basically Q values. So the input for the neural network, the input is all the informations that are related to state, not the reward. Not the reward. We don't have reward at this moment. Reward is calculated. Reward is given by the environment. So all the information about state is an input. But then again, like this one, the certain action it takes based on the state. But this one will learn from these experiences. That's why for this one, state, action with the reward, and then the next action, next state is actually the input to this neural network. Yes.
And my final question is, what are the approaches they use to solve inventory optimization problem?
You mean the method in the optimization problem?
Some
Not only RL, but different other mechanisms?
names of the algorithms.
Oh, okay. So when we talk about optimization, you can have like different mechanism. Mathematics is there again, right, to solve that optimization problem. But then even Q-learning algorithm can be used in optimization. So what happens is we try to maximize the reward basically. So when we talk about optimization, we need to mathematically define whether we need to maximize something or minimize something, right? So based on that equation, we define that problem into MDP. So once the MDP is ready, you can either use Q-learning, you can either use DQN, PPO algorithm as well. So actually, when I had to optimize this inventory management problem, optimize that inventory, so I used DQN, I used PPO algorithm. That time, these algorithms were very popular. Even now it is popular, but I used those algorithms. So, but then again, you need to understand so many other stuff as well. For example, your state, action, they are continuous or not, it is discrete or not, it's huge in number of information or not. So you need to understand different factors. But then again, I think PPO algorithm has a wonderful output in optimization as well, right?
Thank you so much.
Thank you, my pleasure. Right, please. Thank you everyone. Thank you so much for having me here.